Network pairs. Prove that the language d-clique, aka d-clique, is NP-complete. So the language d-clique consists of a graph G and a positive natural number k, such that G has two vertex disjoint cliques of size k. Just as a refresher, let's go ahead and look at some examples of what a clique is. So this is a clique of size 1, clique of size 2, size 3, size 4, size 5. So a clique is just a set of vertices where every vertex is connected to every other vertex. So if you look at any pair of vertices in this 5 clique, they will have an edge between them. Okay, now that we're comfortable with cliques, let's look at what it means for G to have a clique. So here's a graph, and it has a clique of size 4, because if we look at these 4 vertices, they form a clique. It also has a few other cliques. In particular, it has 1, 2, 3, 4, 5 cliques of size 3. Okay, now let's take a look at this graph in the context of d-clique. So d-clique takes in both a graph and a positive natural number. So let's go ahead and turn this into a tuple. What happens if we plug in the positive natural number 4? Is this an element of d-clique? Take a moment and think about it. No, this is not an element of d-clique. We were able to find one clique of size 4, but we weren't able to find two vertex disjoint cliques of size 4. Let's try resetting and plugging in a different number, 3. Is this an element of d-clique? Yes, it is, because we are able to find two cliques of size 3, and they are disjoint. Notice we couldn't pick out, say, these two cliques, because they overlap. They are not vertex disjoint. We have to pick these ones. To drive this point home, let's look at a modified version of the graph that doesn't have this half of it. If we looked at this graph and plugged in the number 3, this is no longer an element of d-clique. Even though it has multiple cliques of size 3, they are not vertex disjoint. Awesome, now that we're comfortable with what d-clique is, let's get on to proving that it is NP-complete. Remember, to prove that something is NP-complete, we need to show that it is in NP and that it is NP-hard. So let's start with the first part and show that d-clique is in NP. To do this, we need to define a verifier v that takes in two things as input. The first thing is just going to be whatever the type of d-clique is, so in this case, g, k. And the second thing is another string u, which we call our certificate. We need to construct our verifier so that three things hold. First, whenever we have a yes instance of d-clique, there must exist some certificate that's poly-sized out there that will cause v to accept on this yes instance and this certificate. Whenever we have a no instance of d-clique, our verifier should always reject, no matter what you plug in for the certificate. And our verifier should run in poly time. So take a moment and pause here and see if you can come up with the verifier yourself. Alright, the first thing our verifier is going to do is check that the certificate u is of the form s, t, where s and t are subsets of the vertices in G. These are going to represent our two vertex disjoint cliques of size k. So we just need to check that they actually are two vertex disjoint cliques of size k. We can check that they're both k cliques by checking that both of them have size k, and that every pair of vertices in them must be connected via an edge. And we can check that they're disjoint by checking that no vertices in S also appear in T. If all three of these checks pass, our verifier is going to accept, and if any of them failed, we will immediately reject. Now we have to just go through and explain that our verifier works as expected. When we have a yes instance of d-clique, we know that our input satisfies this definition and really does have two vertex disjoint cliques of size k. That means you will be able to find a certificate of the form s, t that represents these two vertex disjoint cliques of size k, and by definition, it's going to pass these two checks as well. We know it's going to be polylength because the certificates are just subsets of the vertices in G, which is part of our input. So this part checks out. When we have a no instance of d-clique, that means G does not have two vertex disjoint cliques of size k. That means you will never be able to find a certificate that passes all these checks, so V is going to always reject no matter what you put in for U. Finally, we know that our V runs in poly time, because it just goes through and checks the input, and checking every single pair of vertices in these sets takes at most n squared time, where n is the number of vertices in G, which is poly time. Since all three of these checks pass, we know that d-clique is an NP. So we can move on to the second part, which is proving that d-clique is NP hard. To show that something is NP hard, we need to show that some language we know is NP hard carp reduces to d-clique. It's often a good idea to pick a language from the list you know that looks similar to the language you're trying to show is NP hard. So we're going to go ahead and pick clique. As a reminder, clique is the language that also consists of a graph and a positive natural number, but it just checks that that graph has a clique of that size. To show that clique carp reduces to d-clique, we need to come up with a transformation function f, which is poly time, and satisfies this by implication. that if you have a yes instance of clique, that by implies that the transformed version is going to be a yes instance of d-clique. So take a moment and pause here to try and come up with this transformation function on your own. Alright, let's define this function. As input, it's going to take in a graph and a positive natural number, and we're also going to want to output a graph and a positive natural number. We're going to construct our new graph g' by simply unioning two copies of the original graph g together. And finally, we're just going to return that new graph with the same number k. Let's check that this actually works with the by implication. If we have a yes instance of clique, that might look something like this, where this one is a yes instance because it does have a clique of size 3, then that would mean that the transformed version of this input, so f of this, which is equal to 2 copies of this graph and 3, should be an element of d-clique. And yes, we can confirm that it's always going to be an element of d-clique because the original clique that we had, which we know exists because it's an element of clique, is going to get duplicated and therefore have 2 cliques. And we know that they're guaranteed to be vertex disjoint because we have 2 disjoint copies of the graph. How about the other direction, when we have a no instance of clique? Well, a no instance of clique might look something like this. There are no cliques of size 4 in this graph. So the transformed version again looks something like this. And again, this is not going to be an element of d-clique because we need 2 vertex disjoint cliques. Since there wasn't a clique in the original graph, and it's not possible to have edges across these 2 copies of the graphs to form any new cliques, this is also going to be a no instance of d-clique. When you're explaining this in your proof, you might find it helpful to prove both directions directly or to use the contrapositive. Whichever way you go, your proof should just be clear enough to convince your reader that this by implication checks out. Lastly, we just need to check that our function f is polytime. Well, all f is doing is creating 2 copies of g and then just returning that. This is a linear operation, so we know that f is polytime. Both of these checked out, so we know that d-clique is NP-hard. Since we showed that it's in NP and that it's NP-hard, this means that it's NP-complete and we're done.